I'm Adam from RFOXiA from our real lab. Today we are answering why a supercapacitor charges in under 5 minutes while a lithium battery doing the same job takes hours, and why that difference is not engineering, it is physics. Let's start with the question that almost nobody asks correctly. When you plug in a battery, what is actually happening inside it? The answer is not electrons moving, the answer is chemistry. A lithium polymer cell charges by forcing lithium ions to migrate through an electrolyte and intercalate, embed themselves into a graphite anode. That word intercalate is doing a lot of work here. The ions are not simply arriving at the surface. They are being driven into the crystalline structure of a solid material layer by layer at a rate governed by diffusion. Diffusion is slow. It is governed by Fick's laws and it scales with the square of distance. The deeper the lithium must travel into the anode material, the exponentially longer it takes. This is not a design flaw, it is the fundamental speed limit of electrochemical storage. You cannot charge a lithium cell arbitrarily fast without destroying it, because the lithium ions cannot diffuse into the electrode material fast enough. Push too hard and you get lithium plating and metallic lithium depositing on the anode surface instead of intercalating into it. That is how cells degrade, catch fire and fail. The chemistry sets the pace, and the chemistry is not negotiable. Now consider the supercapacitor. The physics here is entirely different. A supercapacitor, more precisely an electric double-layer capacitor, does not perform any chemistry at all. There is no ion intercalation, there is no diffusion into a solid. What happens instead is this. The electrodes, which are made of activated carbon with an extraordinarily high surface area, but we are talking about 1,000 to 3,000 square meters per gram, which is not a typo, are immersed in an electrolyte. When you apply voltage, ions from that electrolyte adsorb onto the surface of the carbon. They do not enter the carbon, they park on it. They form a thin electrical double layer at the electrode surface, which is where the device gets its full name. The energy is stored electrostatically, not chemically. And because the ions are only moving to a surface rather than through a solid, the process is limited almost entirely by ion mobility in the electrolyte, which is orders of magnitude faster than solid-state diffusion. This is why the MultiNav Pro Plus power kit charges in under 5 minutes. The 1100 farad supercapacitor system is not waiting for chemistry. It is waiting for ions to arrive at a surface. When you connect a 12-volt 5-amp adapter and 60 watts of input, the ions move, the double layer forms, and the system reaches full charge. The physics allows it. Now let us talk about the trade-off, because there is one, and it is important. Electrochemical storage, batteries, achieve energy densities of roughly 150 to 250 watt-hours per kilogram. Supercapacitors achieve 5 to 10 watt-hours per kilogram. That is a factor of 20 to 50 difference in energy density. A supercapacitor is not competing with a lithium cell on stored energy per unit mass. It cannot win that contest. What it can do is deliver and absorb power at rates that would destroy a battery, cycle hundreds of thousands of times without degradation, operate across extreme temperatures, and charge in a fraction of the time. The 18,800 joules stored in this system, calculated from 1/2 times capacitance times voltage squared, is enough to power the complete MultiNav Pro Plus module stack for a full working day. That is the engineering decision, not maximum energy density, maximum operational readiness. The 5-minute charge window is not a marketing number. It is the consequence of removing chemistry from the energy storage equation entirely. When you charge a LiPo for 2 hours, you are waiting for ions to travel through a solid. When you charge this system for 5 minutes, you are waiting for ions to cross a liquid. One of those processes is physically constrained. The other one is not. There is one more thing worth understanding. A standard battery's internal resistance increases with age and cycle count, as that is the physics. Electrochemical diffusion versus electrostatic surface adsorption. Now let me show you the hardware that actually delivers this in the field. This is the 1100 farad supercapacitor bank, the core of the power kit. At 18,800 joules of stored energy, it runs the complete MultiNav Pro Plus module stack for a full working day. Because charge storage here is electrostatic, not chemical, the system accepts a full charge in under 5 minutes. There is no diffusion into a solid electrode. The ions arrive at a surface, park, and the system is ready. That is the entire physics argument made physical. This is the charging adapter, 12 volts at 5 amps, delivering 60 watts into the supercapacitor bank at 4 volts and 10 amps after conversion. At that input rate, the double layer forms across the activated carbon surface in under 5 minutes. A comparable lithium cell receiving this power level would plate metallic lithium and fail. The supercapacitor accepts it without complaint because it is not doing chemistry, it is doing surface physics. This is the power output stage. the side of the kit that your modules actually see. One supercapacitor bank, regulated down to supply the BLE module, the GNSS module, and the sensors module simultaneously for a full day of operation. You charge once in the morning, you work, the system does not ask you to stop because a battery decided to give up. That is the operational consequence of 8800 joules stored electrostatically. This is the integrated ST-Link programmer. It matters here because firmware development means repeated flash cycles. And repeated flash cycles mean repeated power connections, interruptions and resets. A supercapacitor BAT system handles that without the voltage sag or recovery time a battery would introduce under switching loads. The programmer and the power system are designed to coexist on the same bench without interfering with each other. This is the complete connectivity kit, flat ribbon cables, all necessary connectors, everything required to link the BLE module to the power board and the programmer to the BLE module. No adapter hunting, no breadboard workarounds. The flat ribbon geometry keeps the impedance path short and predictable, which matters when you are sourcing power from a high capacitance bank that can deliver current faster than most cables are rated to carry it. Holds less energy. A supercapacitor does not degrade this way. The double layer is a physical phenomenon at the surface. There is no lithium inventory to lose, no electrode structure to crack, no SEI layer to build up and consume active material. The system charges the same way on cycle 100,000 as it did on cycle 1. That is the complete physics of why the Multinav Pro Plus Power Kit charges faster than your coffee brews, and why that is not a compromise. It is a deliberate consequence of choosing the correct energy storage mechanism for the job.